Hi, in this video we are going to talk about the eager implementation of the Prim-Zjarnik algorithm, and basically it is eager because we have to track the content of the heap or the priority queue, and we have to update the edges inside the priority queue if necessary. And that's why in the eager implementation the vertex class has of course a string name, a boolean visited to be able to track whether we have visited the given vertex or not. We have to track the predecessors, we have to store the adjacencies or the neighbors in a list of edges. So far it is the basic implementation. But then we have to track a private edge minimum edge. And basically this is the shortest edge to the actual minimum spanning tree from a vertex that's not part of the minimum spanning tree. And why is it good? Because as we have discussed in the theoretical section, we have to decide on every iteration whether, okay, the new solution can be a better or a shorter path to the minimum spanning tree. So that's why we have to track the minimum edge to the minimum spanning tree from a non-minimum spanning tree vertex. And of course, we have the distance. It is initialized to be positively infinity to detect whether a heap is in need of refresh because of better weighted edge. We are going to see the algorithm itself, it will be clear, but basically this min edge and the distance from the minimum spanning tree are very important properties to be able to decide whether to update the heap or not. And you may pose the question that, okay, for the lazy implementation, we didn't have these parameters, and of course we didn't have these parameters because we don't bother about the content of the heap. That's why it was the lazy implementation. Here for the eager one, we have to track the minimum edge and the distance between the actual minimum spanning tree and a non-minimum spanning tree vertex. Okay, and we have to implement a comparable interface to be able to compare vertices, so vertex objects. And basically this compare is going to return the distance because we have to make the decision according to the distance. Okay, so what about the edge class? It is the basic edge with the weight, the start vertex and the target vertex. We have a constructor, and of course we have the getters and the setters for all the weight, the start vertex and the target vertex. So this edge is the basic edge we have been discussing from lectures to lectures. Okay, so I have created this graph. We have never done it. Basically this graph is going to hide the implementation of the vertex list and edge list related operations and so on. Sometimes it can prove to be useful, sometimes it is not that useful, but basically it is elegant because we can call this graph, and this graph is going to do everything for us in the background. It stores the list of vertices, it stores the list of edges. Basically it supports the add vertex operations, the add edge operation. It's very important because we would like to simulate undirected edges. That's why basically we can construct an undirected edge with the help of two directed edges. We just have to create a forward edge, then a backward edge with the same edge weight. So basically that's why when we add an edge, then we are going to get the start vertex, the target vertex, then we are going to add a new edge with the start vertex and target vertex, then vice versa, the target vertex to the start vertex with the same edge weight. This is how we simulate undirected edges with the help of directed edges. And of course we have the getters and the setters accordingly. The algorithm is the most important part, of course, as usual. So we have a list of vertices. We have a priority queue, the heap as usual, but instead of storing edges, here we are going to store vertices in the heap. Of course the algorithm is going to get a graph. So we are going to get the vertex list to initialize the vertex list itself. The heap is going to be equal to a new priority queue. And basically the spanning tree algorithm is going to iterate through all the vertices in the vertex list. And if we haven't visited that given vertex, we are going to call this prim algorithm. Maybe it's not the best name, this greedy algorithm. I'm just going to rename it Alt-Shift-R to, for example, make prims Yarnik, whatever. Okay, and basically this make Prim's Yarnik is going to get a vertex, because we have specified a vertex here, set the distance to be 0, okay, because we are standing here, the distance from the minimum spanning tree is 0, because we are here. Then we add this vertex to the heap, and while the heap is not empty, first we remove the vertex from the heap. What does it mean? It's going to return the vertex with the minimum distance. Why? That's why we had to implement this comparable interface. Because the heap is going to pose the question that, okay, according to what I would like to sort these vertices, and because in the comparable interface compared to method, we have specified that we would like to compare the distance and the other vertex get distance values. That's why basically whenever we call this remove, which is going to retrieve and removes the head of this queue, it's going to remove the vertex with the minimum distance. And then we scan the vertices. Okay, maybe vertices is a bit better name. So we have a start vertex, we set it to visited. We visit all the neighbors of this vertex via the edges. We get the target vertices, and if we have already visited it, then we continue. We are not going to consider it anymore. And then we have to check that if this edge weight is smaller than this v, so the target vertex get distance, what does it mean? That there's a shorter path to the minimum spanning tree. Then we have to set the distance with the edge get weight, because we know that it is a better solution, a shorter path to the minimum spanning tree. We have to set the min edge to be equal to the edge, and if the heap contains this, so this vertex, then we remove it from the heap. If it doesn't exist, of course, we just have to add it. But it's very important that we would like to avoid adding the same vertex twice to the heap. So that's why first we have to check it. So we remove it and we have to add it again. And basically this is where we update the parameters, so the distance parameters and the min edge for the vertex. And basically this is where we update the heap content. This is what we have been discussing, that for lazy implementation, we don't bother about the content of the heap. We are not going to remove items. We are not going to update the properties of the items in the heap. The eager implementation is going to manipulate the heap content in the sense that we remove items from the heap and we update items on the heap. Okay, so I think it is approximately an elegant solution. So we set visited, we visit all the edges, we check whether we have visited the target vertex that's not part of the minimum spanning tree, and if the edge weights are smaller in the sense that the edge weight is smaller than the actual distance of the vertex, then we have to update the heap accordingly. Okay, by the way, if you have some idea that, okay, maybe this algorithm is not going to be the fastest one, but I think that it is very, very good just to get a good grasp of the eager version of Prim's Yarnik algorithm. So feel free to leave some comments if you have some idea about how to boost up this algorithm. I think that with the help of this priority queue, we are able to boost it up enough, but anyways. Okay, and the show method is basically going to iterate through the vertex list, and if the minimum edge is not equal to null, then we are going to get the minimum edge, and we are going to print it out to be part of the minimum spanning tree. Maybe I'm going to specify that I'm going to show the minimum spanning tree. Okay, and in the application, I will have to use it. So basically, you can download the source code. I'm not going to type it from scratch because it would take a lot of time. What's important that we are managed to create a huge graph with the help of this graph. We are able to add the edges and add the vertices. And basically, if we run the algorithm itself with the spanning tree and the show minimum spanning tree, it is going to show the minimum spanning tree for us. We can make a quick check that we have 1, 2, 3, 4, 5, 6, 7 vertices. So we must have 6 edges included in the minimum spanning tree. 1, 2, 3, 4, 5, 6. So it is approximately fine. I have already checked it, by the way, so feel free to run this algorithm on huge graphs or whatever graphs you want, and then you will get a good grasp of how eager implementation of Prim's yarning algorithm works. What's very, very important, although I don't want to repeat myself over and over again, basically this method, that we have to scan the vertices. And okay, maybe some typo, sorry for that. Okay, it's vertices. So what's very important, that we are going to manipulate the content of the heap. That's why it is called the eager version. For the lazy version, we are not going to manipulate anything as far as the priority queue or the heap is concerned. Okay, so that's all about the eager implementation. Thanks for watching.